Next up, we have Gaurav Madan, who's a doctoral researcher at University of Oslo. And today he's going to present his work on the weakening of the AMOC under extreme climate change.
Great. So my name is Gaurav. I'm a PhD candidate at University of Oslo, working with Ada and Joe, particularly on AMOC, which is in quite a pool of discussions these days. So I'm here to declutter a bit. I was born in 1988, irrelevant. But in 1988, Ronald Stufer and Suki Manabe, who recently won the Nobel in physics, they designed a very simplistic climate model, pretty novel for that time. But now when we look at that model from 2024 perspective, it looks pretty simplistic, 5 degree by 4 degree resolution. You can see the bathymetry, which is pretty coarse here. And it had a few basic components that atmosphere and ocean would interact with each other in these 6 basic blocks. And what they designed was a sensitivity experiment, so to say, how increased carbon dioxide concentration would impact AMOC strength. So what they did, they increased carbon dioxide concentration starting from 1958 and increased by 1% every year. And in one of these experiments, they kept it stable. In the second experiment, they kept increasing by 1% and stabilized it at when it reached double the value after 70 years. And in the third experiment, they kept increasing carbon dioxide concentration further by 1% and stabilized it when it reached the 4 times of the initial concentration. And what they saw, so this is the overturning stream function. On the top, you can see what the initial situation was. It also represents the stable carbon dioxide concentration scenario. The south is on the right side and on the left is north, pretty different than what you see today. And here you see a very well-defined upper limb of AMOC, 16 water flow, more than that. But after 500 years or 400 years of the simulation, that's the length of this simulation, the upper limb vanishes. So there's dramatic weakening that they saw in the strength of AMOC as carbon dioxide concentration was increased. How was that looking in the time series format? So you can see in the stable carbon dioxide concentration, there was some internal variability of carbon dioxide, but AMOC largely remained constant and just had this variability of about 5 Swadra. In 2 times CO2 and 4 times CO2, there was a weakening as carbon dioxide concentration was increasing. When the concentration stabilized after year 70, AMOC did continue to weaken further, but it also recovered by the year 500 completely. But not the case in 4 times CO2. In case of 4 times CO2, the AMOC continues to weaken as carbon dioxide concentration is increasing. By the way, it was stabilized here, the year 140, but AMOC continues to weaken even further, and it does not recover in 500 years. So carbon dioxide concentration does have a direct link with the AMOC strength. And this is something we see in IPCC report as well. This is from chapter 9. Here you can see AMOC strength anomalies based on this mean period. There is some increased strength in the historical period, but as we go in future, what the AMOC strength would be, at least the consensus is there will be weakening by 4 to 8 Swadra. But how much will that be? Again, depends on what scenario you choose and what modeling community you ask. But this weakening trend appears to be scenario agnostic, so to say, that no matter what you do starting from today, no matter what emission scenario you pick, the AMOC is weakening. And initially, I thought this is something to do with scenario, but I was wrong because this weakening is not starting now. This weakening has actually started in the historical period. So do we see this weakening happening even now? Well, the science reports say yes, it is confirmed the major Atlantic Ocean current, and which we define Gulf Stream, AMOC, whatever you want to call it in newspapers, is weakening. This system of ocean currents that transport heat and salt is collapsing, and it could collapse as early as 2025. So if we have some PhD candidates in the audience, I'm sorry, AMOC may be gone before you will graduate. End is near, pack your bags and leave. But that's not the complete story. The last 30 years observations through the hydrographic observations, what we see is there is no change at any latitude at these hydrographic sections that were carried out in the last 30 years. But wait, Historical simulations do show weakening starting in 1980s, but in the observations, we still don't see any signal of this weakening. So this motivated my work that we wanted to figure out why this weakening is happening in these climate models. So here we look at what the overturning stream function, the global overturning stream function looks like in NORI-SM. On the left, you can see pre-industrial control. This time, north is on the right and south is on the left, flip of what Suki Manabe did. You can see a very well-defined upper limb of about 26 water flow, 27 water flow. After 100 years, just like what Suki Manabe saw, the upper limb sort of vanishes. And this is a dramatic weakening of more than 20 Swarter. Just to put numbers in context, 1 Swarter is 1 million cubic meters per second flow, which is, again, to put context, all the fresh water flowing in the rivers on this planet combined. The weakening that we're talking of is 18 to 20 times of that. So it's a huge change that we see in AMOC strength. When we expand this into other models as well, because that was just for NORI-SM, the first thing that we find, the upper limbs location varies a lot. It's all these X's that you see, this represents the maxima of the upper limb for different models. This is pre-industrial. So what we decided, we wanted to figure out and give each model its due chance. The maxima of AMOC is defined as the maxima between 20 to 50 degrees north and 450 meter to 3000 meter depth. So wherever the maxima is in this box will be defined as the AMOC strength. Before we go into what quadruple CO2 experiment do, we wanted to look at what pre-industrial strength of AMOC looks like. And it's all over the place. Here, all these gray lines show individual models. The orange line shows NORI-SM, for which you would see all the plots in future in this presentation. And the AMOC strength can be anything between 14 to 12 Swarter up to 35 to even 40 Swarter ups in some cases. So it's all over the place. Models are showing AMOC in all variety of strengths. And when we take multimodal mean, it kind of hides some of these realities, but this is where we are when it comes to the real representation of AMOC in the models. When we look at the carbon dioxide concentration 4 times the CO2 concentration and look at how AMOC changes relative to its initial strength, we do see weakening. AMOC weakens by about 50% by the year 100. This is a multi-model mean, but when we look at all individual models, just as previously, all these individual models are represented as these gray lines. The orange shows the trajectory of NORI-SM AMOC strength. And after 100 years, if you look at how much AMOC has weakened compared to its initial state, it's all over the place. The weakening can be anything between 14% to 80% in some of the models. So there's a huge array of the huge spectrum of the weakening that you see in these climate models. When I saw this figure for the first time and shared it on Twitter, people were at least happy that the sign of this change is correct. The magnitude, however, varies a lot. So there needs to be some explanation for this huge variation in the magnitude. Now, AMOC is wind-driven, density-driven. We looked at everything, and what we figured out is the surface density change. It changes a lot after 100 years in these climate simulations. On the left, you see the change in surface density. Here, we decompose this change in density because of temperature and salinity. There is huge reduction in the density, surface density in subpolar region, but on an average, there's very little change in subtropical region. And this change is largely coming from the changes in salinity. Temperature does have some role to play, but not as significant. And if you see, these two look very comparable. Now, these two boxes that you see, these are the boxes where North Atlantic current is located. So we calculated the density difference across North Atlantic current, north minus south, and we put that against the AMOC change in terms of percentage, in terms of relative value. What we see, the change in density across North Atlantic current and AMOC change, the strength in AMOC change is strongly correlated. There are some outliers, of course, here, and temperature has a negative correlation, which is so to say that temperature actually increases the strength of AMOC. And salinity, again, looks very similar. When we remove those very high change AMOC strength outliers, this correlation increases to 0.75. So the density difference across North Atlantic current does represent the change in the AMOC strength we see. And there's a pathway, there's a whole anatomy of that, how this process happens in 5 steps. This is a beautiful planet, North Atlantic current shown in right in the red. It's transporting heat and salt from the subtropical regions into subpolar regions. But on the top sits the huge mass of Arctic sea ice. Now, as carbon dioxide concentration increases, there's widespread melting of this Arctic sea ice. And this Arctic sea ice flows into subpolar gyre by these different pathways. The first outflow happens in Baffin Bay, which is also helped by the collapsing glaciers in the Western Greenland. And it all then follows up with the Eastern Greenland additional flow. And this meltwater floods the Arctic basin, the subpolar basin. And this excess flow of fresh water coming from the Arctic just recirculates within the subpolar gyre. And what that, as a result, does, the density gradient across North Atlantic current weakens, which weakens the vertical shear. And the inflow from the subtropics is choked. Given the inflow is choked, the deep water formation, the supply of water that is needed is choked. And as a result, the AMOC weakens. When we look at this as a 5-year slices, the key point of interest here is this tongue of lighter water. Within first 5 years, we see this coming out of northeast of North America. And in the first 5 year itself, you do see signature of weakening North Atlantic current. And here you see AMOC stream function. There's a weakening of about 5 quarter, but close to surface. In the next 5 years, the tongue of fresh water, it strengthens in terms of its density change. It's much fresher. The signal becomes more prominent in the North Atlantic currents weakening. And now AMOC weakening can be seen, which is like about 10 water already within the first 10 years. 5 years further down, this tongue of fresh water is a lot lighter, which means the density difference across the North Atlantic current weakens further, and you can see the surface weakening. And now this weakening of North Atlantic current is spreading in deeper layers, and it's also spreading along latitudes. And by year 16 to 20, the weakening of AMOC is set. There's a lot of fresh water now in subpolar gyre, and the North Atlantic current weakening looks something like this, which is like weakening of 10 centimeters per second or more. Now, this 16 to 20, just to show how much contribution is coming from the density change itself, which is thermal wind. On the left, you see the change in zonal thermal wind in this year 16 to 20. And on the right, you see change in zonal surface current in the same time slab. And the all contribution that you see in these 5 years, slice, snapshot, whatever you want to call it, is coming from the change in the density along the latitudes in the North Atlantic. And now, just to establish my point further, here you see in black AMOC strength in OESM, and in the red is the amount of fresh water in the Arctic, globally average. So as fresh water continues to leave the Arctic basin, you see AMOC strength weaken. And this change in this fresh water is largely coming from the contribution of this changing in the sea ice, the fresh water that was stored as sea ice in the higher latitudes, that is being flooded out of the Arctic basin, and they have only one outlet to go into the subpolar gyre. Now, when we look at the pre-industrial, in the red, you can see is the overturning stream function anomalies calculated from the pre-industrial mean, and in the blue, you see sea ice volume in the North Pole. So they have some internal variability in the pre-industrial. As long as sea ice is stable, AMOC remains stable. Come the historical experiment, you see increase in AMOC strength and increase in sea ice volume. It is often catered to that. This is because of the aerosol forcing. But by the end of historical period, you see collapse in the sea ice volume, and AMOC follows, which goes further on even into the future scenarios. So sea ice collapses first. This sea ice flushes this subpolar gyre with this excess fresh water that you can see even in historical simulation, but towards the last 20, 25 years. And AMOC continues to weaken, and this weakening continues further. And how much is this related? In blue, you see density difference across North Atlantic current. And in the red, you see this AMOC strength anomalies. These are monthly values. Here, this is pre-industrial. Everything is kept constant. Both are very well aligned. At the month 6001, carbon dioxide concentration is quadrupled, and immediately density difference changes across North Atlantic current and AMOC follows. So these anomalies are tied up closely even to the month-to-month values, not just year-to-year or multiple decades as we saw. But the good news is sort of that even when there's huge freshwater outflow, AMOC does recover after 1,000 years, but that's still a long period and sort of idealized scenario. But there are more pathways that lead to recovery, which is another paper that we are working on at the moment. This was idealized scenarios, what the future looks like. What's the future for AMOC in next 5 years, not next 1,000 years. Here we do see, as per WMO report, weakening of between 1.5 to 2 Sverdrup in future in the next 5 years. So AMOC is not collapsing by 2025, so you can relax a bit. There is some weakening, yes, for sure. But again, as we saw in the pre-industrial simulations where models were struggling to get the AMOC strength right, we do see a similar scenario here. While ensemble mean shows a very nicely looking even weakening, but when we look at all the contributing models, how much the weakening is, again, it depends on who you ask. If there is an even weakening, because some of the models like these MPI and IITM, ESM, they do show some strengthening as well. So what's next for us? I have no idea. Maybe weakening, maybe not. But again, the lack of observation that we still have, the longest time series that we have for AMOC is just 25, 30 years, which is way too low. If I want to summarize what we found in this particular research was, as the planet has excess greenhouse gases, it warms, ocean currents shift as a result. The warm whispers of North Atlantic current become cold and slow. And as the ice continues to melt from the glaciers, from the sea ice, the silence of North Atlantic current grows. So you can scan this code if you want to go deeper into the manuscript where we go into full array of analysis of 35 different models and help yourself. Thanks a lot. I'm happy to take the questions.
Thank you very much, Gaurav. That was great. Maybe slightly worrying for you, people like me who live in Scotland that could drop by quite a lot. So Helene's got a question.
Okay, thank you so much for that talk. I have loads of questions. I could talk to you at great length about this.
Yes.
So I just a few remarks is that, well, first it was great to see a photo of Ron Stauffer and Suki Manabe there, and maybe getting Ron or somebody to give a retrospective seminar would be great. You know, as you know, I was one of the authors on chapter 9,
Yes.
and you know, I would say the assessment in that chapter of the AMOC was incredibly difficult. You know, there's lots of conflicting evidence, as you've pointed out, between the observations and the models and the spread in the models. So, you know, super difficult, and I really hope with AR7 we can make some really good progress in that. So you know, I'll read your paper as well. It looks great. I have a few questions. When you talk about this, the anatomy that you laid out, do you think that's generalized for all models, or, you know, we've seen in our kind of we have models at different resolutions for the ocean, and for example, the low resolution
Has everyone lost Helene's sound there?
Yes. I
Helene,
thought
we've lost your sound for a minute.
Sorry, did I drop out?
Yeah.
Yes.
Okay, sorry.
So we heard you into the resolution.
Maybe the last minute.
Yeah, how much does it depend on, like, the, you know, like in different resolution models, you can have the convection to the south of the ridges or in Labrador Sea, and I just wonder, you know, we've seen big differences in those sort of resolutions, so I wondered if you'd address that.
Well, as you remember your own plot from chapter 9, we see that as you increase resolution to even 0.25 degree, the weakening of AMOC that we see even amplifies, right? So this is one of the things that was key feature. But the 5-step anatomy that you saw in the presentation, this general representation of what we see as a common feature among the models. But again, there are some models which show different the way this Arctic meltwater flows out. Like in some models, so what really dictates the amount of weakening that we see, it depends on how fast this fresh water is leaking the Arctic, how much it is, and what pathways it takes. So these 3 things matter, right? So if this water diffuses into the southern or subtropical North Atlantic quickly, which is what you see even when the AMOC recovers in those long simulations, the amount of weakening that you see and for how long it stays weak, it varies a lot. Again, Labrador Sea in models dominates when it comes to overturning compared to eastern subpolar North Atlantic, but from observations from OSNAP, we do know that's not true. It's eastern subpolar North Atlantic that largely governs the strength of overturning and the deep water formation. So, but then there was a paper by one of the groups in US actually, Annalisa Bracco's group, where they increased the resolution to 1 degree in Labrador Sea, and they could see the convective volume reduced by 85%. So increasing the resolution does show positive results, so to say, but at the same time, it demands 1 kilometer or low resolution in those regions, which is remarkably difficult to achieve when it comes to global simulation and for the time period that, as per IPCC requirement, we looked for 150 years or something. So this is a struggle still to get the freshwater outflow right, to get the interactions right. And since it's so tied up with the resolution that we follow, honestly, I don't see there will be much change in representation of AMOC weakening in CMIP 7, but I keep hope for CMIP 10 or something.
Yeah. No, it would be great to see new approaches, you know,
Yes.
perhaps with the you know, localized increased resolution, perhaps in Labrador Sea to try and resolve this.
But resolution can be the answer if we are going finer than 100, 112, 116th, 120th, then it is the answer.
Yeah.
But anything less, I don't think there will be much change.
Oh, we can't hear you, Eleanor.
Sorry, Michael, if you've got your hand up there. Sorry.
Yeah. Last year, after one of these high-profile publications came out, there was a very popular kind of discussion page by Stefan Rahmstorff on Real Climate about AMOC, and in it he was kind of pointing out that perhaps a couple of papers and pointing towards CMIP models. He phrased it as overestimating stability of AMOC and kind of not having tipping behavior in maybe that's related to resolution or something else. Do you think it's possible that all CMIP models are missing the instability and tipping behavior in AMOC?
But there's one feature that CMIP model generally has is the monostable nature of AMOC, which is widely talked about earlier as well. But at the same time, NEMO models behave slightly differently. The climate models that have NEMO as their ocean model. So again, this is still a topic which is pretty much open for discussion. I don't have any conclusive evidence to whatever I say prove it, but there is large variation in that. And I'm particularly looking forward to what NEMO does in future, and also this unstructured grid like that Alfred Wegener Institute's climate model uses, FISOM, how that would be helpful in these global simulations, given the unstructured nature allows you a lot of flexibility to increase resolution where you want and not get into all those nesting things. So I think these kind of simulations will give you a better overview of how things would change or how stable AMOC is. But is AMOC too stable? The general consensus appears to be yes, but again, I personally can't comment on that.
Great. Final question from Julie.
Thanks so much for a really interesting talk. All the talks have been great. My question, so there's a group led by Gavin Schmidt trying to come up with a historical meltwater forcing for CMIP 7. And so I'm just wondering if you could speculate on how that might feed into the simulation of the historical AMOC, because it seems like it it was reproducing the limited observations you have. And so then having this additional meltwater forcing how that might change. And then I guess thinking about Antarctic sea ice extent and how crazy it's been in the last year. And I know the CMIP models melt all the sea ice in the Antarctic, in a lot of it in the historical period anyway, which was not realistic, but any speculation on how that might be, I guess, how the Southern Ocean part contributes to the changes you see?
So answering your second question first, there is often discussion of seesaw when north weakens, southern overtakes and kind of maintains the balance. Weakening sea ice in Antarctica, which has not quite been as discussed of late compared to what's happening in the Arctic basin. That would have some role to play, of course, because that would change the strength of ACC and the overturning that's happening in the southern shores. In these models, we do see the strength of Southern Ocean winds and also Southern Ocean overturning also weakens as north is weakening. So there is weakening happening in both the hemispheres, at least in the abrupt quadrupole CO2 simulation experiments that we saw. So even if Antarctic sea ice alone is reducing, that's again a question that needs a completely different approach to answer. But coming to the first part of your question, if we get the historical freshwater outflow right, how would that control the AMOC in the past or the wading sea in the historical simulation? So this increased strength that we see in the historical between 1850 to 1985 or something, that the group in Reading, that they presented the idea that it is as a result of the aerosol forcing that we see. But again, what it misses out is the freshwater, how historical freshwater looked like. And that's another beef that I have with paleo community, that we do not have a correct representation of the salinity either when it comes to historical time periods. So if we are struggling to get the salinity in historical periods right, I'm sure that the struggle would continue into the freshwater domain as well. But I really hope this experiment does work out and we have some realistic representation of freshwater from the past. So we have some overview of how AMOC looked like in the past, so that we can connect the dots and see where we are in this current 30-year period. Because if you see, AMOC is much more stable, as we just discussed earlier, that in the climate model is a lot stable. Since its time period of variation is so huge, we do not know where this 25 period of observation is in that huge time variation. So is AMOC weakening? Is AMOC inching that tipping point? Is AMOC already in the tipping point? I mean, this is anybody's guess at this point, if we take the climate models out of the discussion. But when we bring them back, then we have some idea that there has been certain changes based on whatever observational record we have. But are they enough? This is a question that I think as scientific community we need to ask. And that's where these realistic forcings of freshwater and other things, they become really, really helpful to understand the past so we can predict a bit better future.
Yeah, I guess the actual measurements of freshwater, anomalous freshwater, are difficult to get prior to the sunlight
Yes.
era as well. So, but yeah, no, thank you. That's great.
Here's
well,
another
thank
thing
you,
I want
everyone.
to
sorry,
I want to add one last thing to this. The weather in Western Europe is something which, or the cold wave in Western Europe is something which is often discussed with AMOC, because the heat transport in the north would weaken as AMOC would weaken. But I think this idea largely comes from the simulations where we have a constant pre-industrial climate, the carbon dioxide concentration. But I think as humanity, we have progressed so much, we have pumped in so much carbon dioxide that I don't think we need to really worry about that much. The excess greenhouse gases will make sure that you are pretty warm. There will be storms here and there, but the total collapse is something which I do not see. And that's what IPCC report also says. It's very unlikely.
Thank you.
Thank you.